reach top. Makes me nervous.
Okay, so I'll let you talk about your presentation.
Thank you. So yeah, my name is Arjun Roy. I'm the last one standing between you and your lunch. So I'll try to make it quick. Okay, so I'm a PhD student at Freie University Berlin and also like an employee in L3 Research Center. This is a joint work with my supervisor, Eleni Dutzi, who recently moved to Munich. Yeah. And the title of this work is Learning to Teach Fairness-Aware Deep Multitask Learning. So let's see what we learn, what we teach. An outline of my talk today. Basically, like I will first try to introduce like what is fairness-aware in terms of like a multitask learning setup. Then we'll try to see like how it was solved and like what are the problems in the existing setup. Then what we do basically to solve that and like what we propose to do. And then like in the methodology, based on our proposed solution, how we develop the algorithm, what kind of algorithm we develop, and then we test our algorithm and the results against the other baselines to validate like whether our algorithm works or not. And finally, we will conclude what to take, what we miss, maybe, yeah. So let's see. I will mostly skip this slide because like now you already know like what and multitask learning is basic. But one thing I want to point over here is like that in the current set or in this kind of setup, multitask learning is basically solved as weighted sum laws, where these weights are actually trade-off weights, which controls how much a task dominates the other. Basically, like it's like a trade-off between the tasks. Okay, so that like one task do not dominate the entire like optimization. Let me introduce what a fairness is, like fairness learning is in the single task learning setup. Okay, so you may notice that like the boundary like over here that was figured by this algorithm is much different from the boundary like what we see over here, because like it has some other objectives as well. Let me first try to explain it with an example with this particular task itself, like why this kind of adjustment in the boundary is needed by this model. Suppose this task like of smile detection, it was trained on certain image data, let's say, like which can be divided into demographic groups of males and females or whatever. Yeah. So now you didn't learn this boundary, but like you learned, your model actually learned this boundary. Okay. What happens? It's very accurate. Let's assume like the boundary is very accurate, and some phone company, mobile smartphone company, actually takes your algorithm and deploys it in its selfie camera. Let's say. So you smile, the camera takes a selfie. A man buys that kind of phone, takes selfies. For example, let's say again, the girlfriend or the wife of the man comes, tries to take the selfie. It doesn't work. The man is in deep trouble, right? But anyways, like joking apart, like this is actually a very serious issue. We can find in the real world example as well. Like we have already seen like the compass data set that was being, or like the compass, like the algorithm actually, like that was discriminating in terms of race. And then there are cases of like, for example, the Amazon being discriminating in terms of geolocations and etc. So this is a very social issue which is like inscribed in our society. Already we have a lot of biases in our society. We don't want algorithms to make further biases, right? So what we do is like that we need another objective inside our optimization. So this is again like, okay, let me say like, first define like what this objective will actually do. There are different ways of measuring fairness in the output. But one of the most popular definition is equalized odds. And how it measures fairness is basically like it tries to measure the absolute difference between the two positive rates between the two demographic groups plus the false positive absolute difference of the false positive rates between the two demographic groups. Okay, and this should be as much closer as possible to zero to have like a fair system, right? Okay, so this is again like solved as a weighted sum loss where the weight is actually attached with the fairness loss. Basically, like it's again like is kind of a trade-off parameter which tries to dictate like how much the fairness loss should dictate the overall optimization. And yeah, this can be regarded as intra-task trade-off weight. So I think like by now all of you have understood like what would be like a fairness aware problem in the MTL setup as well. Like basically like there is an MTL which needs to shift its decision boundary, likewise to make fair predictions in each and every task. And this is like again solved as a weighted sum loss, like, or you can say is like that weighted sum of a weighted sum loss, right? So there are two trade-off parameters that is involved here. Okay, so what is the problem with this kind of thing? So first of all, this kind of setup actually assumes that like fairness and accuracy are always competing with each other. Like improving one might like mess up the other. This might not always be the case, right? For example, say like if I make a like an algorithm which is 100% accurate with this kind of definition, it's always fair. So why I need like to make this competing? It might compete sometimes, it might not. So basically what I'm trying to say is like that it depends on the current position of the algorithm, whether it needs fairness corrections or not. Okay, so, and again like we already know, like whoever is like familiar with the literature of MTLs already knows that like when we are solving a weighted sum loss kind of formulation to solve our MTL, the performance of the MTLs are highly dependent on like correct configuration of this kind of trade-off weights. And in this kind of particular fair MTL setup, this problem become double. So now we need to figure out like twice the number of hyperparameters as compared to or in contrast to like a normal MTL setup. So, and again like the only similar work that that was proposed before us tried to solve this or find these trade-off weights as hyperparameters, that is like with cross validation, and then assuming that like the fairness accuracy balance will never change throughout the training. So basically like they fixed it, but like that can also be like a problematic, like the fairness accuracy balance again also depends on the current position of the algorithm or of the model itself. So we need like what I'm trying to say is like that we need something dynamic. We need to adapt based on what is the current position is, right? So basically what we propose is some kind of a dynamic solution. What I'm trying to say is like that first I'm trying to we try to propose that like we will like check for each and every task what needs to be done now at the current epoch, whether the model needs to be trained for this current task at this current epoch on accuracy or on fairness. Based on that we will make some informed decision. And so in this way, like we get rid of that like that lambda trade-off weight that we were seeing earlier in the formulation. Okay, so now we only have this only one single trade-off weight, and we will also try to configure this dynamically also. Like we will try to also learn this trade-off weight rather. Okay, so now we know like we want this kind of a dynamic optimization, and what algorithm we propose to implement this. Our algorithm is basically based on a student-teacher network, okay? But the student is basically like the fair MTL that we want to learn. The teacher is the one who makes the decision. So the decision of the teacher impacts the learning of the student, right? And the teacher over here, what we choose is an RL agent or rather a deep Q network. Because the only reason for making such selection is because like that we want the decisions to be some kind of informed way. And the RL agent can basically look into the future, like theoretically as much as we want, but like we look one step ahead only to see like in the future, if I make this decision, if I take this action, whether fairness and accuracy both improves or not. So yeah, like and based on this like suggestion, the student updates itself and then like send some feedback. The feedbacks will be like taken as like a reward function, or like these are the rewards that the teacher will utilize to update itself as well. So we see like we have a collaborative training. The student and the teacher are training each other, learning from each other. And this is the depiction of our algorithm basically. And like what are the input states to the DQN model are the like the task specific parameters. Basically what we say, the state of the student in the current task is basically its task specific parameters or the weights. So that is being given as the input to the DQN, and the DQN basically tries to predict what are the Q values for each every like state action pair. So for each and every action, it will try to predict what would be the Q value, and based on that, like whatever Q value means like that what would be like a future value of this current state if certain action is taken. Yeah, in more or less this way. So the student will or the teacher will suggest like whatever for whatever action the Q value is maximum for this given like state. The teacher will try to suggest that action to the student, and the student will adopt that action. This was very important actually, because like everything was more or less dependent on this. If the teacher didn't had a good reward function, then like the teacher would be giving like very bad suggestions, and if the suggestions are bad, the learning of the student will itself be bad. And so we wanted to actually like find like what would be a good reward function. And our intuition was basically like the principle based on which we made this decision is that like we will only positively reward the teacher only and if and only the accuracy and fairness of the student in the current task both improves. Otherwise, like we do not have a positive reward. Okay, and like I mentioned, is also like that we want to actually also learn the trade-off weight. So we do that using this amazing algorithm called grad norm. And basically like it tries to compare like the like gradient norm of the current loss and compares it with the average gradient norm of all the tasks basically. So it dictates that the gradient norm of the current task should not be much different from the average gradient norm. So that's how like it computes the weights, what should be the weights or the trade-off weights, the single trade-off weight. Yeah. So we have discussed what is our algorithm. Now we see like how it evaluates. To evaluate our method, we basically use two different kinds of data sets, a tabular and a visual. The tabular data set is like a very recently published census data, which had like 5 well-defined tasks on their on their GitHub repo itself. So these tasks are not defined by me; it's already defined by them. And for the visual data set, basically like we have different protected attributes. So like we had gender as protected attribute as well, and we could have taken like age as protected attribute as well. But you see like there are different number of tasks for that. Why is that so? I give you one example. Like when I selected gender as a protected attribute, did like facial beard, presence of facial beard made any sense as a task? Obviously not, right? So because like the females, the images will not have. So that's why like in this way we identified certain tasks and we eliminated them for a given protected attribute. And we followed the same for both the cases, like one with age and one with protected. For measuring our performance, we used relative averages. What I mean by relative is like compared the performance of the MTL against a fair HTL trained on the particular task, on that same task, right? And this how like, and then we measured the averages and the baselines that we use. We did this for both accuracy and fairness, measuring both. And the baselines that we use, like first like is a vanilla MTL, which is basically MTL trained with the grad norm update. The second one was the seminal work that was proposed recently. The third one is like a greedy mechanism version of our own model, where the decisions are made greedily instead of like an informed decision. Okay, so we see we compare in comparison to all the baselines in all the datasets. Basically, like we outperformed everyone. With an exception that like in the tabular dataset, ACS pumps, we were outperformed marginally by the vanilla MTL. And yeah, we'll see later like why. We'll try to justify why. So basically, like these kind of averages or whatever like average metrics can be actually like influenced by a single task as well, right? Like if you have some in certain task a very high or very low performance, then it can like impact the entire average itself. So we wanted to also actually check like how our performance was distributed across the task. And over here we wanted to find like whether we have like for our case, for our algorithm, whether we have high whiskers. That is like in certain tasks, like we have very high performance or a very low performance, or we have relatively low whiskers and like the median for the fairness we wanted actually to be lower, and the median for the like the accuracy wanted to be higher. So we checked that for all the experiments, and what we find is like that like among the competitors we do not have like, first of all we do not have like comparatively we do not have that much high whiskers as other competitors have, and secondly like our median is also like very close to what we wanted, basically like a low median for like this equivalent or violation, and high median for accuracy. We wanted to see like what kind of pattern the decisions were coming, what kind of pattern the teacher was actually following for making the decisions, and how it impacted. We wanted to basically study that, like how it impacted, how can it impact our performance. So first we observed in the like the tabular data that like it was making a balanced decision, it was evenly choosing like both fairness and accuracy all the time. And then we try to like intuitively figure out like what it actually helped. Basically, like you see that like we were outperformed in accuracy by the vanilla MTL. That means like that for this particular model to for this particular data set to achieve the best accuracy, we always needed to train in terms of accuracy. So otherwise, like it was no way possible to reach the best accuracy. So that's why like we have certain sacrifice in the accuracy, but like we also make good improvements in terms of fairness, and this is the reason why, like because like we also like incorporate fairness in the decision making, or like take fairness loss sometimes. In the celebrate data set, in both the experiments, we see like the performance is actually or the decisions are actually unevenly distributed. Like in some tasks, for example, say accuracy loss was selected more number of times. In some other tasks, fairness loss was selected more number of times. And in the experiment, particularly with this age as protected attribute, we see like in certain like in many tasks, a certain loss was selected at a stretch. That means like that correcting for a particular loss, and then like it tried to correct the another loss. Okay, and if we see basically like the box plots, you can see like in many of the tasks only like treating with accuracy basically was more than enough. So we did like fairness was not basically that much important in those kind of tasks, or like fairness loss, like correcting with fairness loss was not that important in those in certain tasks, but like in certain other tasks it was very much important. And you can see that like there are high whiskers for the vanilla MTL. That's the reason why. So yeah, that's the reason we can justify like why this kind of pattern is observed in the selection of in the decision making of the teacher. So I will try to conclude now. Okay, so in contrast to rigid fairness accuracy trade-off formulation, dynamic loss allows some flexibility, of course. And the teacher network allows to basically look forward and make an informed decision. That's why like we have a better decision in comparison to the greedy. And yeah, like we also reduce the number of trade-off parameters that was required to half, basically. And our experiment also showed like we did that effectively, right? Like we were able to do some effective, marginally, or like at least comparable, and sometimes also improved performance over the baselines. And yeah, the selection of the baseline actually was the selecting of the best loss was actually like effective in producing such results. We saw that like in the pattern charts of the decision making. Some self-criticism that I have, basically like this kind of setup is highly dependent on finding the correct like reward function. So if the reward function goes wrong, everything goes wrong. So this has to be improved somehow. And all the tasks we are jointly training. Like basically like we have a shared representation, then we have individual layers. This may not always be like the best possible scenario. So like that's why I was asking you like how can we group. So basically like we need to figure out like certain good combinations of group. And the complexity, because like if you see the runtime complexity, if you think now we have a RL on top of a DL. So the runtime complexity is very high. So somehow we also have to like control this. So these are the self-criticisms that I have. And yeah, these are the references. Thank you for your attention. And I have one more advertisement to make before I change. Okay, so, like we have like a lot of open positions. So please write if you are interested to work with us. Yeah. Okay, thank you.
So we have time for one quick question before lunch. Let me say.